Okay, so 2378. In binary coded decimal, you do each individual digit its nibble representation. So what's a 2? 0010. What's a 3? 0011. What's a 7? And what's an 8? There shouldn't be a long way. That shouldn't give you the same answer. So you just thought it's the same answer just because yours has zeros and ones in it? Mine is comprised of zeros and ones, therefore it must be correct. So this is very similar to how we used the nibble format to go between binary and hex, right? Okay, so for binary coded decimal, which is what you worked on for your homework assignment, what you looked at for your homework assignment, we take each individual digit and we get its nibble representation. Now, can we do math with binary coded decimals? Is this a mathematical representation of 2,378? So kind of to prove our point for Nick over here, this is the ones place, the twos place, the fours, the eights, the 16s, the 32s, the 64s, 128s, 256, 512, 1024, 2048, 4096, 80, what was it? 80 something, 16 something, 32 something, 32,768, probably this one. So if we added all those up, would we get 2378? Well, ones, twos, fours, eights plus 16s plus 32 plus 64 plus 256 plus 512 plus 1024, 2048, 4096, 8192.
Oh, we're already bigger.
So 8192 plus 512 plus 256 plus 64 plus 32 plus 16 plus 8 gives us 9,080.
Yeah, close enough.
Sorry.
Round number.
You got an 8 in there, you're close.
Got an 8 in there, you're close. All right, so this is not a mathematical representation of this decimal number. This is a binary coded decimal representation. Okay? Now the question it asks is, can you do math with this? The answer is sort of. Okay, only if you're doing multiplication by 10. Okay? I'll show you what I mean by that. So, this would have been the answer to the quiz. Just a whole bunch of nibbles, one nibble for each digit. Make sense? Now, your homework assignment was to create a converter in Java. We're supposed to write a method, Bcd to decimal, and another method, decimal to Bcd. So now Bcd to decimal should take in a string representation and give us the decimal version of that string. Correct? Okay, so here's our hex to bin, bin to hex. All right, this is just going to confuse things. Let's just get rid of all that crap. Because I like deleting gold. All right, so we'll go ahead and do this in main. So we're going to have a static string BCD to decimal. I'm sorry. BCD to decimal should return a int. And it should take a string as a parameter. So we're going to pass it in a string that should be a legal BCD nibble. And what do I mean by legal BCD nibble?
Or
0, 9. Okay, the legal decimal digits, right? We can represent larger values than that in a nibble. What's the largest decimal number we can represent with a nibble? 15. Largest decimal number we can represent with a nibble is 15. Legal decimal digits are 0 through 9. Okay, so if we assume this is a legal nibble, it's going to be the binary representation of one of the digits between 0 and 9. Okay, so what are you supposed to do in BCD to decimal? Well, we're supposed to convert whatever BCD you passed in to its decimal equivalent. Well, a couple different ways we can do this. We already had some code for converting binary to decimal, right? So we can repeat that. So, we can go and call it, but we'll just go ahead and write it in place here. So I'll say place is equal to 1, sum is equal to 0, for int I is equal to s dot length minus 1, I is greater than or equal to 0, I minus minus, so we'll walk from the end of that nibble towards the beginning of that nibble. Each time through, if s dot char at I is equal to a 1, then we'll say sum plus equals place. Every single time, we will multiply place by 2. So place starts off as 1, then it's the 2's place, and it's the 4's, and it's the 8's for our nibbles. And if we see a 1 in the particular place, we're going to add place to our sum.
But are we walking through nibbles?
Hmm?
Are we walking through nibbles?
Yeah.
Are we walking through one at a time? If you're
What do you mean only walking through one at a time?
You're only walking through one character at a time. So,
Yeah, in this string.
and
So
then-
if I had the input that looked like this,
Oh, okay.
which that's 9, correct?
Yeah.
So this is the 1's place plus the 8's place
Right.
for a 9.
Thought we were doing like double nibbles.
No, this doesn't even assume. This would work generically for any binary number, really.
Yeah.
We're just assuming this guy's a nibble that's an illegal BCD number. So in the end, sum is our answer, so we can return sum. So we'll go ahead and test that. So we'll do a system.out.println test.bcd to decimal. We'll pass it 1, 0, 0, 1, and this should print out a 9 for us, right? Zero 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 1 1 should give us a 3, so on and so forth. That make sense? Now our code as is technically will work on things bigger than a decimal number. So this is going to give us a 15, but that's actually not a legal BCD. So how would we account for that inside of our code? Well, if sum is bigger than 9, that means it was not a legal BCD digit, right? So we might write a little if statement. If sum greater than 9, maybe we just give them a warning, system.out.println, not a legal BCD nibble.
I missed the L.
I missed a who?
The L in Println.
Oh, thank you. Similarly, at the very, very beginning, what if we had a length that was greater than 4? That guy's not a legal nibble to begin with, right? So we can print that out. Now, in either of those cases, what might we return? If it's not a legal nibble, we could decide we're going to return -1. Maybe that's just our code for bad input, similar to the index of method. If sum is greater than 9, we'll give them the error message. We'll return a -1 as well. So now we're going to give them 1, 1, 1, 1, and it'll go ahead and do the conversion and get a 15. But in the end, it's going to notice, oh, 15 is too big, so it's going to print out not a legal BCD nibble, and then return a -1. That makes sense? Similarly, if we give it a number that's too big, it'll yell at us and say, that's not even a nibble. All right, so that makes sense? This guy works for legal binary coded decimal nibbles. So that's BCD to decimal. The other thing you were supposed to write is static string decimal to BCD, and this guy was going to take in an int val as a parameter, let's say. And this guy should create for us a nibble. Now we might ask right off the bat, if val is less than 0 or val is greater than 9, this is not a legal decimal digit. Right? And maybe we return null, or we can return the empty string. So if the conversion can't happen, we'll just return the empty string. Let's say that. Otherwise, we need to do some converting. And how do we convert a val? If we're here, val is a legal decimal digit. So how do I convert a decimal digit into its binary equivalent? Nick, you might be able to help us with this one, seeing as you did it on your quiz. How do I convert a decimal number into a binary number?
Use the whatever number you have and divide it by 2.
Okay, keep dividing it by 2 and doing what with the remainder?
You record the remainder because that's the nibble.
Okay, that's the bit that goes into building the nibble. Okay?
So you divide, say, 9 by 2, and you get remainder 1.
So on and so forth. Okay? So, 9 divided by 2. Let's just do it over here. So if we had 9 divided by 2 is what? 4 with remainder 1. 4 divided by 2 is 0. How many times is, is 2. 2 times 2 is 4 with remainder what? 0. 2 divided by 2 is what? How many times does 2 go into 2? 1 time with remainder 0. How many times does 2 go into 1? 0. 0 times 2 is 0 with remainder 1. Then we read our answer from bottom up. 1, 0, 0, 1. Make sense? So we need to write the code, which we've done before, that solves that same problem. So we'll say string answer is equal to the empty string. While val is not equal to 0, we'll say answer is equal to the empty string concatenated with val mod 2. So that'll record the remainder, right? And then we'll say val is equal to val divided by 2. And we'll keep whittling down val, recording the remainder each time. And the reason I'm recording it, I'm saying answer is equal to this. So I'm not even done yet. Concatenated with answer. We're putting our remainder on the front. That way we can build this thing backwards, which is the order it's supposed to be built in. So we'll record a remainder first, tacking it onto the front of answer each time. Then we'll update the value of val to make it half of what it was before using integer division. After this while loop, what do I have? Do I have the binary version of the decimal val? Is it necessarily in a nibble? For instance, what's the decimal version of the value 0? I'm the binary version of the decimal value 0. It's 0. What's the binary version of the decimal number 1? 1. What's the binary version of the decimal number 2? 1, 0. None of those are nibbles. What's a nibble? 4 bits. Nibble is 4 bits. So I need to look at my answer, and if it's less than, I wouldn't even be here if I didn't have a legal decimal number, right? So I know that at most, my string is going to be 4 digits, 4 bits. But if it's not, I need to tack some zeros under the front of it. Correct? Let's say it was 3 bits long. How many zeros do I need to tack on? 1. Let's say it was 2 bits long. How many zeros do I need to tack on? 2. Let's say it was 1 bit long. How many zeros do I have to tack on? Okay, how did I figure that out? I took 4 and I subtracted from that the length. So we'll say 4 int I is equal to 0. I is less than 4 minus, it's not s, it's answer. Answer.length I plus plus, and I have a, there we go. So this will be, if answer had a length of 3, 4 minus 3 will be 1. This guy will go through 1 time. If answer had a length of 1, 4 minus 1 will be 3. This guy will go through 3 times. Okay? But we're going to see a problem here. So what am I going to do each time? I'm going to say answer is equal to the string 0 concatenated with answer. Why does this break?
It never ends
Why?
because you keep on making answer longer.
I keep changing the value of answer, and then I'm using it in my Boolean expression. Does that make sense? So we might want to have something like this. Int num zeros is equal to this guy. Before we start modifying answer. So now we'll say I is 0, I is less than num zeros, I plus plus. So in the end, we will return our modified answer, which is guaranteed now to be a nibble. Make sense? We'll go ahead and test that. We'll go ahead and pass it a 0 for starters. We would expect this to give us a 0, 0, 0, 0. There's our 0, 0, 0, 0. We passed it a 7. We'd expect it to give us a 0, 1, 1, 1. There's our 0, 1, 1, 1. What if we passed it a 13? We'd expect it to scream at us, and I think we chose to return the empty string. Not a legal decimal digit. And we also handle negative numbers. So if we said -1 here, which is also not a legal decimal digit, single digit, not a legal decimal digit. Make sense? All right, so these two methods allow us to convert between an individual decimal digit, that is a legal digit in decimal is 0 through 9, and its BCD nibble equivalent, and vice versa. So now if we had something like our quiz question today, convert this into its BCD equivalent. If we wrote a function to do that, what would that function look like? Well, it's going to return a string, right? And we'll call this number to BCD. Since we called this decimal to BCD, we probably could have called this decimal digit to BCD, but whatever. So we'll call this number to BCD. This guy will take an int num as a parameter. And we want to build the full BCD equivalent of that number. Every single decimal number can be represented in BCD, correct? Ints in Java only accept collections of decimal digits, 0 through 9s. So every single decimal number can be converted into its BCD equivalent. And what do I do? Well, I'm going to calculate the nibble for each of these digits. How do I go through each digit of this number? So if number, for example, was 2378 as an int, go ahead.
Convert to a string.
All right, let's make this guy a string to begin with. Empty string concatenated with num. Now our beautiful integer is now a string. Now we can work with it. Remember, Java is a string-based language. Once we can get something into a string, it's malleable. I like that word, malleable. It's a good word. All right, so does it matter if we walk through this guy forwards or backwards? As long as you concatenate right, not really, right? Because this isn't a math thing. We're just converting each individual digit into its BCD equivalent. So let's create a string answer. Start that off as the empty string. We'll say for int I is equal to 0. I is less than temp.length. That's the number of digits in our number. I plus plus. Each time through, what are we going to do? We're going to say answer is equal to whatever answer currently is concatenated with test.decimal to BCD. And this guy expects us to pass it a decimal digit. The problem is I have temp.charat I, which is a char. How do I get that guy back into a digit? So I have a char. So in this example, I have the char 2. So I'm looking at something that looks like that. And my decimal to BCD requires this to be an int. So how do I turn the char 2 into an int? The int 2. Go ahead. Integer.parseInt. Okay, what does integer.parseInt take as an input? String. Okay, so I need to convert this guy into a string, then call integer.parseInt.
Yes, sir.
Okay, anything else I can do? That's true. So I can say integer.parseInt. And pass it the empty string, concatenated with that. Okay. Now, those of you who are in 250, we learned a couple of new tools today. Maybe you could help us out. How else might I do this? We know for a fact that temp.char@I is a char, and that char is either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Correct? I'll even take the non-250 people if they want to give me the solution I'm fishing for. How can we use index of to solve this problem?
Make an array in a string.
Make an array in a string. You're in 250. Do you know anything about arrays yet? Huh? Yeah, but I'm asking the 250 questions right now. Do you know anything about arrays in 250? So if I'm asking 250 students, probably not what I'm fishing for. How can we use index of to solve this problem?
What if you have a string called map with just 0, 1, 2, 3, so on to 9, and do index of that?
Maybe that guy? We'll take the string 0 through 9, and we're going to find the index of this digit. If that digit's a 0, what bucket is 0 found in? Bucket 0. What if this digit was a 9? What bucket's that 9 in? Position 9. That make sense? This is a string of length 10. Legal buckets are 0 through 9. Index of will map this char to its decimal equivalent using the index. That make sense? We didn't do any weird math conversion. We just took advantage of the knowledge that if we put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 together in a string, those guys are indexed 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We can take advantage of that. And then in the end, we will return answer. So now we can say test.number to Bcd, and we'll pass it 2378 as an int, our number. And that guy gives us our Bcd equivalent, which should be forgot it gives it to us, and well, here, I'll just put it in there and we'll highlight it. Same value, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. Same number. All right, that makes sense? How we wrote that converter? Okay, why would we use Bcd? So all fine and dandy, we can do it. You know, we really liked hex to binary and binary to hex because that was legitimate. You know, it was like the right numbers, correct? It was a shortcut. We didn't have to convert binary to decimal, then decimal to hex. We didn't have to convert hex to decimal, decimal to binary. We could just go directly from binary to hex or hex to binary. It was perfect. It was the perfect conversion. It just so happened that nibbles could represent the numbers 0 through 15 as the max. But now when we start dealing with decimal numbers, which have legal digits of 0 through 9, 10 legal digits, and we're going to use nibbles for that, we have a problem. Well, what if we, instead of using nibbles, we used 3-bit numbers. Is a 3-bit number enough to represent all the decimal values? It's not. We require a 4-bit number, right? Because a 9 is 1001. So we need a 4-bit number in order to solve this problem. So why BCD? What's the purpose? We have all sorts of nibbles that are illegal BCD digits. 1111, illegal. So any nibble that's going to represent 10, 11, 12, 13, 14, or 15 is going to be an illegal BCD nibble. So why use BCD in general? What's the perk of it?
Doing code numbers and screwing your friends.
Because I hate my friends.
Randomly post your phone number online anywhere you want.
Kind of like the t-shirts that say, you know, there are 10 different kinds of people in the world, those who understand binary and those who don't. How many of you didn't get that before this class? How many of you still don't get that? 10 is the binary number 2. 2 different kinds of people. Okay, so besides screwing with your friends, why might we be interested in BCD? Okay, why?
Because when you're doing the computation in the computer itself or in the electronic device itself, it will do it in binary and then it will convert into decimal for the user to read.
Okay, so I think you're saying something good, but I think you're meaning something good, but you said it poorly. So you said for displaying numbers, right? Human beings are not going to like looking at it like that. From a displaying perspective, we like to see the actual decimal number. Because humans like decimal. But computers, as you point out, like storing stuff in binary. Right? It kind of makes sense for them. Now, is this a binary number? Careful. Is that a binary number? Okay, it's 4 individual binary numbers. I suppose you could say, yes, this does represent a binary number, but the binary number it represents has literally nothing to do with the binary number we're interested in, right? Or has nothing to do with the decimal number we're interested in. So this is 4 separate binary numbers, all glued together to give us a binary representation of a decimal number. So really the convenience of this is for storage, correct? It's storing values as a binary representation. But it keeps us from being able to do math with those numbers, with a little exception. So let's start off with a, kind of a simple little example. We'll do it on the same screen, I guess. Let's say that I had the number 10. Okay? And I want to do this. This is a binary coded decimal. What would the binary coded decimal be? 00010000. Correct? That's the number 10 in decimal. Now, when we take our 10 in BCD, binary coded decimal, when we take 10 and we multiply it by 10, what do we get? 10 times 10 is 100. All right. What's 100 as a binary coded decimal? 0001 00000000. What do we have to do to multiply by 10? Just concatenate 4 zeros onto the end. So it's actually very good for doing multiply by 10 math. We didn't actually have to do any math. We just tacked on an extra nibble. Okay, what about divide? So what's 100 divided by 10? 10. And what did we do to get to that? Took off 4 zeros. But what if we divide it by anything else? Only tens. Only the magical number 10. Okay, so it has a very limited mathematics ability. So really, we should only think of BCD as a storage representation when we don't need to do math with something. Okay, last time we talked about this a little bit. Like, how many times have you ever added 10 to your social security number? Or multiplied your phone number by 2? Those aren't numbers we do math with, right? Those are numbers that are representative to human beings with decimal digits, but computers don't like storing things as decimals. We like storing things, well, they like storing things as binary values. So it allows us to take a decimal value that we don't intend to do math with and encode it as a binary number or a binary looking number, as long as we know not to do math with it. So, advantages. Any mathematical operation based on a factor of 10 is simpler. We saw that. Decimal to binary conversion is fast and requires little code. We just wrote it. So, example, we saw this already. To truncate around a BCD value, you need only 0 the appropriate nibbles. Because of this, BCD is often used in financial applications due to their need for very accurate numbers. So we can actually deal with things after the decimal places if we treat those as binary coded decimals as well. You know, we can truncate something by just zeroing out those nibbles. So everything becomes concatenation. We're not actually doing any math. So, disadvantages, as we said, unless math is based on a power of 10, operations are more complex and require more hardware. Don't store things that you want to be mathable, which we decide is a word, right? Coined it, Lippmann word, mathable. Okay. It is, probably not.
I submitted with BD.
Did you credit me?
No, of course not. You didn't copyright that shit.
So, spoken like a true student at a Christian university. What would happen in your other classes if you made a comment like that?
Good question.
So let's put yourself in front of one of your Bible classes. Dr. Jastrom's up front, and you drop one of those answers. What happens?
What did you ever do?
I don't know, when was the last time you saw theology prof murder a student?
Okay, so in any case, don't do it with mathable crap. It also is not a compact design. I mean, so it's not as compact as unsigned binary. It may take more memory to store the same value. I mean, potentially, if we have a value that we're converting to BCD, that value may actually have a bigger footprint, rather. It might actually have a bigger footprint than if we just took that decimal number and converted it to unsigned binary using Nick's quiz method. So we might not actually save space. So why do it? If it doesn't have a smaller footprint, why should we do it? Well, Nick's our example. It was tough for you to do that quiz in under 2 minutes, wasn't it?
Yeah, I was rushing.
Yeah. Until you saw the answer, you realized 2 minutes was like plenty of time. Converting between decimal and binary coded decimal is super fast. So we're maybe throwing out this idea of, oh, we want to squeeze it into a little tiny footprint. Because if we want something in a little tiny footprint, what do we use, Abe? Hex. Hex goes into a little tiny footprint because it's memory crap, right? Yeah, he's got this. I don't like the grin that's on there. What's up? Yeah, he's just thinking about forking. Inside joke if you're not in the operating system class. Forking in what?
Spawning out child.
Yeah. You're forking children. It's actually what it is. And then if you build the Reaper program, you can then go and reap them.
All is said by the picture.
I think that's Christian worldview. All said by the patriarch. Things that came out of the patriarch's mouth in class. I want to talk a little bit about forking children.
Have you seen the whitest kids you know? The greatest.
Which one?
The greatest.
I think I have, yeah. The one I remember the most is the spelling bee one, right? So I heard what you said. I like that one. All right, so we're not looking for efficiency from a footprint perspective. We're looking for algorithmically quick representation of decimal values. Make sense? What about BCD signed numbers? At this point, we've only talked about unsigned numbers. Unsigned numbers are easy. It's like, well, we don't need to worry about decimal place, or we don't need to worry about plus or minus signs. Just everything's a positive number. Well, now we got to deal with negative numbers. So BCD signed numbers, no set standard, since different hardware manufacturers use different methods. So now when you start dealing with signed numbers, we have some fluctuation in how it's actually done. Easiest way is to append a nibble to the left-hand side representing a positive or negative number. We could use one of the illegal nibbles to represent positive and another to represent negative. That is, 1010 is a illegal nibble, right? What's the decimal equivalent of that? That's 10. 10's not a legitimate decimal, or not a legitimate BCD nibble. So we can have, take 3 of them and say these mean positive, and take another 2 and say these mean negative. Okay, maybe BCD values preceded by 1111 typically mean they are unsigned. So we use that last one and just say, anything with 1111 in front of it means it's an unsigned number, so treat it as such. So we're kind of building in, we're using our extra nibbles to encode some meaning into our BCD values. So if our BCD value is preceded by 1111, that means this is not a signed number. Or I'm sorry, this is an unsigned number. If our BCD value is preceded by one of these 3, it's positive. If it's preceded by one of these 2, it's negative. Now this actually causes some confusion. This kind of gets back up to with the set standard thing up here. Let's just say you're not working with signed numbers necessarily, and the person is reading your BCD value. Well, if they have 1111 in front, how do they know that 1111 means it's unsigned as opposed to 111 being part of the value? It's a trick question.
Because if they know it's a BCD, then they know that 111 can't be part of the value.
111's illegal. If it's there, it's either an illegal number or it's representing that it's an unsigned value. Right? Those are our options. Okay, but we do have some standardization problems. If you're trying to read something, if something is representing values in a binary coded decimal and it's feeding those values into a program that you have, you might have to determine whether or not it's encoding them as unsigned by default or if it's going ahead and throwing the 1111 in front, meaning unsigned. You might have to do some experimentation to figure out how this guy inputs. And it actually becomes kind of an interesting thing. Hardware is a little bit different than software. Bad Quiz Nick over here was helping me with a program earlier today. And, it's a program that's worked for a while. And then all of a sudden it just started crashing. It's a piece of software I wrote. And after some debugging, it turned out that the data source had changed. The format of the data it was feeding me was no longer in the format that it used to be in. Well, that is very common in software because you can't control the other side. But in hardware, it's probably less common. Correct? Because a lot of times you're controlling both sides of the equation. But now when we take this one step farther, we start bleeding this class together with the operating systems class. Typically, we have a piece of software that lives between our hardware and our operating system. That's called a device driver. Right? Your device drivers are pieces of software. And what if your device driver changes the way that it feeds your operating system information from the hardware? Now all of a sudden software that's maybe taking advantage of it starts having problems. So that's where standards become kind of an interesting animal to grapple with because you can have things start crashing, and we've seen this before. We've all experienced this when there's a little software update that you think has nothing to do with something, all of a sudden an application stops working. We mostly see it in our mobile devices because we're very app focused on those. But sometimes the smallest thing changes that we don't think has anything to do with anything else, outside of some small little PDF bug fix or something like that. And all of a sudden some non-PDF type application is crashing because they changed this, which broke this, which broke this, which broke this, which broke your app. Does that make sense? So standards become kind of an interesting thing. So something to consider when you're working with technology. All right, binary counting. The use of binary counting sequences is common in digital applications. Very common, right? I mean, we like to count. Human beings go 1, 2, 3, 4, 5, 6, 7, 8, 9. We might assume that counting in a computer application or a piece of hardware is probably going to do the same thing, but it's going to do it in binary, right? So, for example, an n-bit binary value could be used to represent the position of a, not phrasing, rotating shaft as being within 2 to the n different arcs. All right, so we might utilize a binary number and count. So, think of this like kind of this could be a thing for a wheel in a car. As it rotates, that means that the axle is in a different position. That makes sense? Okay, so we might want to count for that. So we might say it's in 2 to the n different arcs using an n-bit binary value. So if we're doing this in nibbles, it would be 2 to the n, 2 to the 4 different positions that we can represent. And how many positions is that? 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. 16 different positions is what we can represent with a nibble for this kind of example, right? So we're going to use a 4-bit binary number to represent 16 different possible positions that this axle can be in. And that might be of interest to us for whatever application we're using. I mean, I assume that maybe for Abe it would be more of like a pottery type thing, like the pottery wheel.
Sure.
Oh.
Position, rotating shaft.
This guy kind of have you. Oh my God, I'm going to hell.
And on
Christian worldview.
video.
Well, that was Christian worldview, though. I'm pretty sure what I just said is biblical.
I'm just saying, we encapsulated that moment.
That's we encapsulated that moment.
In next class, we need to learn how the rotating shaft connects with forking.
Oh, it was him that was telling me he was watching my my videos at lunch today. He was telling me he watches my videos, and him and his cousin Ali just sit there and laugh at these. Well, you can't pay for this kind of it. Well, you can. It's high tuition, but it's worth it when you get this level of entertainment.
Do you get extra YouTube views of just random people
Why do you think I put ads in them? It's not as lucrative as you think. I think I made something like 28 cents all last year. It's just garbage. And I don't have my bank account connected to my Google account, so they couldn't even pay me. I got an email letting me know we're holding this cash.
You gotta have $10 before you see, you have to make the titles of your videos more creative. Give them a hint as to what's inside, other than just this is this class on this day. This is this class on this day. Intro to forking.
Continuation of forking with rotating shaft.
And then what? As you're still frame up a picture of a puppy wearing a diaper or something like that.
Position of a rotating shaft within 2 different arches.
Arcs.
Oh.
Arcs. Can you even read?
I read good.
All right. As the shaft turns. A sensor can determine which of the arcs, I'm going to start leaving some words out here, can determine which of the arcs it's currently lined up with. So if we're thinking about this as a tire on a car, we might be interested, there might be a sensor, and then we're interested in what's the current position of the tire. Okay? So where it's aligned, we might read a digital value and associate with one of those specific arcs and do something with that. Okay? In that particular case, we're not necessarily doing math on those numbers. We're more interested in, is this in, if we're thinking about this like humans, is it in position 0, 1, 2, 3, 4, 5, so on and so forth, right? Out of 16. And maybe if it's in position 16, we do this. And if it's in position 8, we do this. We respond to those different positions. We're not necessarily doing math with it. It's more informational to us. So maybe by remembering the previous position and timing the changes, we could also compute speed and direction of if we're dealing with a vehicle here. So these might be interesting things. But what's the problem with that? What problem might you run into if you have, and this kind of gets back to something, we're connecting some dots with an earlier discussion we had a couple of weeks ago about sampling theory. So we have a sensor that's going to be constantly reading from this position. And as that sensor is going through, we're trying to figure out which arc position it's currently in. Well, what if it doesn't sample at the exact same time it's in that position? What if you miss a position? That could be problematic, right? That would be a bad thing. We talked about this, when we dealt with our computer screens, and we talked about refresh rates. We talked about this with a lot of different things where we can miss data. When we were dealing with like Wi-Fi with 2.4 gigahertz, we need to make sure that our antennas that are inside of our laptops are sampling that radio frequency often enough so that data is not missed, so that we don't, so that we can receive our email and stuff like that. Okay, so here's a picture. And this is counterclockwise, Abe. All right, so in this example, they're using 3-bit numbers rather than nibbles. So we're able to have 8 different positions, right? So 1111 is 7. So 0 through 7, 8 positions. All right, so we're able to keep track of 8 different positions here. So we can have divided. This is all what we've already talked about. So we can take the 360 degrees divided by 8. So each one of those positions represents a 45-degree arc that we're reading it from. Just making up some example. All right, make sense? So one type of sensor, this is used for like disc-mounted brakes, used and dismounted, with slots cut into the disc at different radii representing different bits. So something that looks like this. Okay? Light sources are placed, so maybe it uses a laser sensor, are placed on one side of the disc while sensors on the other side of the disc detect when a hole is present, i.e. the sensor is receiving light. So this guy shows a disc that might be used to identify the shaft position of the example from the previous thing. So you see we have these different slots in here, and each one's kind of a different length, and we'd have a sensor that's just going to read how the light's coming through. All right, so that might be how our sensor's reading this. And you think about this, if it's on a vehicle, and you're going 65 miles an hour down the interstate, how often are we going through these different positions? Often, right? Okay, so this is an interesting issue. So in its current position, the slots are lined up between the second and third light sensor. Let's look at that real quick. Well, I don't think you can actually see it on there the way they're saying. Let's just take it as this. So are lined up between the second and third light sensor, but not the first. So the sensor will read a value of 110. Okay? Go back here. Yeah, see, I don't think you were...
Is the first sensor at the bottom?
I think so, but you can't really tell where this one is, necessarily. Let's just roll with the example. Okay, so currently it would read a value of 110, or position 6. Okay? Now, real quick, let's just go back here. Notice that the way this counts is 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. More than 1 bit often changes between positions. So that might be some extra work to do that conversion. Does kind of make sense? And this is kind of where our problem comes in. So it's possible to sample the sensor at the instant when more than one gap is open or closed between the light source and the sensor. So some bit changes may be recorded while others are not. So now it's not even a matter of we didn't sample often enough. Now it's a matter of we might have sampled part of the problem, but not the second part of the problem within a single time frame. So we detected 2 of the bits, but not the third. And now our numbers are completely off. We might have read position 6, but it's actually position 2. Not even related to each other. Does that make sense? So that's where something comes in called gray codes. So gray codes, kind of like binary coded digits, but even more, I guess, arbitrary. So these are an alternate counting sequence used where only 1 bit changes between values. So for example, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, so on and so forth. Okay, only 1 bit changes between these. So this guy to this guy is 1 bit. This guy to this guy is 1 bit. This guy to this guy is 1 bit. This guy to this guy, 1 bit. So at most 1 bit's changing. This kind of connects us to something we're going to talk about in the operating systems class called atomic operations. What is the smallest operation that can happen so that we don't run into something called race conditions? Okay, so if only 1 little bit changes each time through, we're at least hopefully giving ourselves the best chance of not misreading data. So again, this is not mathematically correct, just like BCD, but even less mathematically correct than BCD. BCD is at least somewhat mathematically correct as long as you're doing things with powers of 10. But as the shaft turns, only 1 bit will change, and that's a good thing. So there exists an algorithm to convert an n-bit unsigned binary to its corresponding n-bit gray code. And this is what the algorithm looks like. So we're going to add a 0 to the left side of the unsigned binary. There should now be n boundaries between the n plus 1 bits. So if we look at this here, if this is our unsigned binary number right here, 100011, we're going to add a 0 to the left. Now notice how they have these little upside down carets here drawn before. These are boundaries. So here's a boundary, here's a boundary, here's a boundary, here's a boundary, so on and so forth. Okay? For each boundary, write a 0 if the adjacent bits are the same, and a 1 if the adjacent bits are different. So in this case, 0 and 1 are different, correct? So we'll write a 1. 1 and 0 are different. We'll write a 1. 0 and 0 are the same. We'll write a 0. 0 and 0 are the same. We'll write a 0. 0 and 1 are different. We'll write a 1. 1 and 1 are the same. Write a 0. That make sense? The algorithm for converting a binary number into its equivalent gray code. Now notice the gray code that came out of this was 6 digits, 6 bits, just like the original value was. So this extra bit that we threw on the front was really unrelated to the final value. What it did is it gave us that one last boundary to work with. Kind of make sense? Okay, so what we want to do, and just to give you a heads up here, we're almost done with this slide set. This is your homework assignment at the end of that slide set. It's a nightmare. Okay, so let's write conversion algorithm that goes from, and that assignment's so hard too, it's awesome. So, here, let's delete all this crap because this is garbage, right? We don't need that. Do you know how many years it would take me to write that? All right, so what's up? How many hot pockets? Okay, so we want to write a converter that takes a unsigned binary number in and produces the equivalent gray code. Actually, I'm sorry, I started it wrong. Static string bin to gray, or bin to GC. That sounds more legit. Gray code, GC, get it? Haha. And this guy will take in a string binary number as a parameter. Now, what does the algorithm say to do? Right off the bat, it says tack a 0 on the left-hand side. Cool. So we're going to say bin is equal to bin is equal to the string 0 concatenated with whatever bin is. So we threw a 0 on the left-hand side. Make sense? All right, now we need to go through and wherever the boundaries have adjacent characters that are the same, we record a 0. Wherever they're different, we record a 1. So we're going to be recording that in our answer going left to right. So we'll have a string answer. It starts off as the empty string. Now, we know that we're going to be comparing bucket 0 to bucket 1, bucket 1 to bucket 2, bucket 2 to bucket 3, bucket 3 to bucket 4, so on and so forth, right? Produce our values. How do we guarantee that we have an even number of boundaries? So for instance, if we come back here, what if this number was originally 7 digits long instead of 6? Would adding the 0 to the front still be okay?
Yes.
Okay. Why? What does that 0 really do? Let's think about the purpose of that 0. If we didn't have that 0, we're going to compare the 1 to the 0. So this is bucket 0 to bucket 1 to bucket 2, bucket 2 to bucket 3, bucket 3 to bucket 4, bucket 4 to bucket 5. How do we know to stop? As opposed to 0 to bucket 1, 1 to bucket 2, 2 to bucket 3, 3 to bucket 4, 4 to bucket 5, 5 to bucket 6. How did we know to stop?
We have the length of the string.
The length of the string tells us how many times to go through. If we need to create a gray code that is the same length as the original string, we need to tack that extra 0 to give us enough boundaries to produce that exact length. Make sense? So, we'll start off, pos 1 will be 0, pos 2 will be 1. How many times are we going to go through? We're going to go through bin.length minus 1 times. Why minus 1? Because I've already added the 0 on. I made it longer than it originally was. Make sense? So we'll say for int I is equal to 0. I is less than bin.length minus 1. The only reason I'm saying minus 1 is because I just arbitrarily made it longer than it used to be. This is how many gray codes I need to produce. I'm going to generate a gray coded digit bin.length number times based on the original length of bin. Notice in the example here, the gray code version of this had the exact same number of digits in it as the original input. Make sense? And then I++ each time through. Now, we're going to be recording our answer inside of answer. So, if bin dot charat pos 1 is the same as bin dot charat pos 2, if they are the same character, what do we do to answer? If they're the same, we record a 0. If they're not the same, we record a 1. Each time through, pos 1 plus plus, pos 2 plus plus. So originally we compared 0 to 1, then we compared 1 to 2, then we compared 2 to 3. So both those numbers increment each time. And finally, return answer. So now we can test this. System.out.println test.bin to GC, and our binary number is 1011. So that's what we'll pass it. And this should give us the gray code value 110010. 110010. That make sense? So pretty simple algorithm to turn a binary number into its equivalent gray code. Kind of make sense? All right. Here are some examples of gray codes. So derivation of the 4-bit gray code. So binary starting with an extra 0. So these are 5-digit nibbles producing 4-bit gray codes. So notice that the first several are the same. We get to the second one, only 1 bit changes. In this case, 1 bit changed, 1 bit changed, more than 1 bit changed. So when we went from here to here, this bit changed, and this bit changed. So 3 bits changed between these two. But when we went from here to here, stayed the same, 1 bit changed. See the benefit of gray codes? Okay, now, homework assignment. I had to squeeze the font way down for this. Make that plain text. All right, so we have a bunch of questions similar to what we've been doing with quizzes and stuff like that. So for instance, what is the minimum number of bits needed to represent this value using an unsigned binary representation? What is the largest possible integer that can be represented using a 6-bit unsigned number? So on and so forth. All right. So there are 14 questions. The very last one is create the 5-bit gray code sequence. That's similar to what we have right here, which is the 4-bit gray code sequence. You can do this by hand if you'd like, or I might recommend typing in our program, passing it all the binary numbers between, all the 5-bit binary numbers and getting the gray codes, and then just copy that from your output screen and paste it into your homework. Make sense? All right, so
Why are you giving us an
early midterm. No, the midterm's gonna be way harder than this. Way harder than this. All right, so I'll put this up on Angel. This is due on Thursday.
How do you want all of that submitted?
Word document. You can, or you can just paste it into the thing if you want. Bye.